Okay, so welcome to the BK topology seminar. So it's a great pleasure to have Darrick Lee today from EPFL. So he's going to tell us about topological approach to signatures. So Darrick, please take it away.
All right. Thank you very much for inviting me to this seminar today. As Chen mentioned, I'm going to be talking about a topological approach to signatures. So just for a bit of context, my background and my current research is in applied algebraic topology. And I know I'm going to be speaking to a peer group today. So I think I'm going to try to talk about sort of motivate some of the applications of this work as I'm going through some of the material. And so just as a broad overview of what this talk is about, the overarching goal is to develop some notion of monomials for mapping spaces. And so monomials are fairly classical objects when we're just talking about, for example, elements of Euclidean space Rn. But what we want to do is to think about how can we get some analogous notion for mapping spaces. And specifically, we're going to be focusing on Lipschitz spaces of maps. And to just motivate some of this, I'm going to go through some, just very quickly. If we think about the case of d equals 0, so this is just ordinary monomials in Rn, I can think about the collection of all of the monomials on Rn using this map P, which is an element of this formal power series. And what I'm doing is I'm just taking essentially iterated tensor products of each element. And so I'm thinking about this formal power series as a power series of symmetric tensors. And so, as I mentioned, the components of this power series, once we fix a basis of Rn, are just ordinary monomials. And this is extremely useful to study functions and measures in a very classical sense. So if we take a normalized variant of this power series map, which I'll denote using this P bar, this map is continuous and injective. It's universal, meaning that linear functionals in this Hilbert space are dense in the space of continuous bounded functions. Now it's bounded because of this normalization procedure. And you should kind of think of this as some analog of like the Stone-Weierstrass theorem. And additionally, it's characteristic, meaning that if we take the expectation of this power series, and this corresponds to just taking the collection of moments of some probability measure on Rn, this expected power series map is injective. So looking at these monomials allows us to study nonlinear functions on our domain, on Rn using linear functionals in this Hilbert space. And it's also characteristic, meaning we can talk about measures on this space also as elements of this Hilbert space. Now, more recently, this notion of monomials has been generalized to the setting of path spaces. And this is an object, this is done using an object called the path signature. And this is something I'll be introducing later on. But we can think about this as a map from the path space into a formal power series of tensors, which we also think about as a Hilbert space. And this object has had wide applicability in both machine learning and in stochastic analysis. So in machine learning, we often want to study sequential data. So things like time series, where we have some collection of features that vary in time, and we want to understand what are the relationships between those these sequences. And in the last 20-ish years, the path signature has also found wide applicability in stochastic analysis, and this is through the development of something called rough paths. And one way of thinking about rough paths is that it provides a deterministic integration theory for highly irregular maps. So imagine things like Brownian motion. Using this theory of rough paths, we can sort of talk about deterministic integration theories for these objects, rather than probabilistic ones such as like Guido integration or Stratonovich integration. So I'm saying all of this mainly just to highlight that the main applications for this work are in machine learning and in stochastic analysis. So just to give a broad outline of the talk, I'm going to just give an introduction to path signatures. And as I'm doing this, I'll talk about its applications to machine learning. And then we'll go into Chen's iterated integral cochain construction. And this is sort of where these path signatures originally arose in about the 60s and 70s, when Chen was looking into studying the topology of loop spaces from a sort of de Rham theoretic perspective. And finally, we'll talk about how we can use this topological perspective to extend this notion of signatures to higher dimensional domains. All right, and I just want to start off with a sort of basic data science example. So I mentioned that the path signature can be used to study time series. And so this plot is what something I have in mind. So here we have two functions that are varying in time. And we can qualitatively see that there's some lead lag behavior between these two time series. The dark blue time series is leading the light blue one. And in fairly simple cases like this, there are classical methods such as cross-correlation. This is just taking the convolution of these two time series. And we can use this cross-correlation to sort of detect this lead lag behavior. We can look at the peaks of this cross-correlation to see, okay, there is this, we can use this as some sort of signature that there some of this lead lag behavior is going on. And additionally, we can sort of tell what the time delay is. But one of the limitations of the cross-correlation is that it's inherently parameterization dependent. So if I reparameterize the time axis, this nice peak that we saw earlier on sort of plateaus out, and we can no longer get this nice signal of lead lag behavior, even though in the original time series, this is still happening. And the fundamental reason why cross-correlation can't detect this is the fact that lead lag behavior is something that is reparameterization invariant. It only depends on the order in which events happen. Does something happen before or after something else? Whereas cross-correlation really depends on the parameterization. And so one way to fix this is, rather than thinking about these as just time series, I want to think about this geometrically. So what I'm doing here is I'm just plotting these two time series, gamma 1 and gamma 2, and looking at the image of this path. The image of the path itself is going to be reparameterization independent. Oh, sorry, parameterization independent, because the parameterization just tells us what the velocity is. And so by studying geometric properties of this corresponding path, we get reparameterization independent features of the underlying time series. So one feature that we can use here is to look at the signed area. And so the signed area is just the integral of the winding number if we have a closed path. And if we apply Stokes' theorem, then we can write it in terms of these iterated integrals. And I'm just going to suggestively write this into these two integrals as S12 and S21. And so the point here is that we want to look at geometric features of the path to detect reparameterization invariant features. And in particular, the signed area gives us some notion that there is some of this lead lag behavior going on. It traces out this ellipse, and if we have some cyclic behavior that goes that repeats itself, but may not be periodic in the sense that it has a specific period, we can use this signed area as an indicator of lead lag behavior. And so these two iterated integrals are actually just part of a larger family of iterated integrals. And all of this is collected into one object called the path signature. And so I'm just going to give the definition here. So let's say that we have some path in Rn, and we're going to assume that this path is Lipschitz for now. I mean, for this whole talk, we'll be working in the Lipschitz setting. And given some multi-index, I1 up to Im, where each of these indices are just some number between 1 and the dimension of the path, a dimension of the codomain, we define the path signature of gamma with respect to this multi-index as this iterated integral. So we're integrating the various components of this path, the derivatives of various components of this path in the order specified by the multi-index. And we can collect all of this information into the path signature, which we view as a map from the Lipschitz space of paths into the formal power series of tensors. And so the original definition was given by Chen in the 50s. At this point, he was mainly studying, he wanted to characterize those paths evolving over manifolds. But as I mentioned, this led to the development of rough paths by Terry Lyons in the late 90s. And so in this Lipschitz setting, I just want to go over some of the metrics that we can use, because this will be used later on. By Rademacher's theorem, this says that any Lipschitz map is going to be differentiable almost everywhere. So we can think about the derivative of the path as just some L infinity function. And moreover, since the path signature is only defined using the derivatives, we can actually talk about a quotient space of these Lipschitz maps. So we say that these two paths are translation equivalent if their derivatives are the same, and we'll denote these equivalence classes using this tilde. And there are two standard metrics that are used in the analytic setting. There's the one variation metric, which can be formulated for Lipschitz paths as just the L1 norm of the difference of the derivatives, and also the Lipschitz metric, which is just the L infinity norm. And it turns out that there are more invariance properties of the path signature. Specifically, it's reparametrization invariant, which is one of the reasons we introduced this. So if I take some Lipschitz monotone increasing bijection that reparametrizes the time axis, the signature is going to be invariant under this. And in fact, the full invariance of the signature was characterized as something called Treelike equivalence. So if we have two paths, gamma 1 and gamma 2, we say that then the signature of these two paths are equal if and only if the two underlying paths are tree-like equivalent. And so one way to think about this, I guess in this setting, this is the definition for piecewise smooth paths, is that if we take two paths and they differ by a finite number of retracings, where retracings are just these parts of the path that sort of jut out and then retrace back along itself exactly. If it differs by a finite number of these retracings, then we say that they are tree-like equivalent. So this was originally proved in the piecewise regular setting, where paths are piecewise C1 by Chen in the 50s. And later on in 2010, this was extended to the case of bounded variation paths by Handley and Lyons. And additionally, there are some algebraic properties of the path signature. The first is a sort of internal multiplicative structure. So if I take two multi-indices, I and j, then the product of these two signature terms can be written as a linear combination of higher order signature terms. And this is formulated using the shuffle product. And so just as an example, this is the higher order terms are given by all of the possible shuffles between the multi-indices I and j. And the main point I want to make here is that with this property, we can start to see some similarity between these signature terms, Si, and ordinary monomials on Rn. And the similarity is the fact that we have this product structure, namely the signature terms or linear combinations of these signature terms form a subalgebra of the continuous functions on a space of Lipschitz paths. And so I'm going to start calling these signature terms Si as path space monomials. And then in the next slide, I'll give some more motivation behind this terminology. But there's also a second algebraic property of the path signature, and this is Chen's identity, which is sort of an external multiplicative structure. This says that if we have two paths and we look at the concatenation, the signature of the concatenated path is just going to be the tensor product of the corresponding signatures. And in particular, we can think about the signature as a group homomorphism from the space of Lipschitz paths, quotiented out by this tree-like equivalence into the tensor algebra, where the group operation in the domain is just concatenation, and the group operation in the codomain is tensor multiplication. In particular, this gives us a way to compute the signature of the inverse path or the time reverse path, which is just going to be the tensor inverse. And so one of the reasons this is very useful in the context of machine learning is because this signature has two very nice properties, which are these universality and characteristicness properties that I talked about with ordinary monomials. And specifically, this is useful in the context of what's called kernel methods. So this was work that was done by Ilya Shevirev and Harold Oberhauser in 2018. And here I'm going to be looking at a normalized version of the path signature, or a normalized and parameterized version of the path signature. So at this point, we can just think about this as we have some modifications on this signature map. And often in machine learning, we want to study sort of two different types of data, which is looking at functions on some input space or measures on this input space. One example of studying functions is if we want to study some sort of classification problem. If we have a collection of multivariate time series, and let's say that these have binary labels. So in this picture, I've just denoted this using red and blue. Can we find some continuous function on this input space into R that acts as a decision boundary for these labels? So a decision boundary we can think about as just the level set at f equals 0. So can we find some function that can separate these two classes of data with just this level set? And it turns out that the signature is a very useful tool for studying such problems because it's universal. This means that the linear functionals, when we think about this as functions from the path space into R, these linear functionals are dense in the space of continuous bounded functions on the Lipschitz path space. And again, these are bounded because of this normalization procedure. And what this means is that we can use these linear functionals to approximate decision boundaries arbitrarily closely. And in practice, this allows us to use linear classification algorithms to do nonlinear classification. The second type of problem that we want to study is to look at measures on the path space. So a specific example is something called the two-sample hypothesis test. So if we take, let's suppose that we have two probability measures on the path space, and we have samples from each of these two probability measures. How can we tell if these two probability measures are the same or not? And once again, the path signature has a nice property that allows us to do this in a very efficient way, and specifically that it's characteristic. So this means that the expected signature is injective. So if we take the expected signature, all of these expected signature monomials, we can use these to completely characterize underlying probability measure on the space. And in particular, we can use the norm on this power series of tensors as a metric for these measures. And so going back to these two properties of monomials that I talked about earlier on, that these monomials can approximate functions and characterize measures, we find that the path signature actually has these two properties. And in particular, these are extremely useful properties for studying both functions and measures in machine learning. And so what we would like to achieve is to get something like the path signature for maps from higher dimensional domains. And so in order to do this, we're going to sort of go back to the topological origins of the signature in terms of Chen's cochain construction. And so just as an overview of this, Chen's construction, this was originally formulated for path spaces and loop spaces. He constructed a sort of cochain algebra model for path spaces that are that's a subcomplex of the de Rham complex on the path space. Sorry, I forgot to mention that in this section too, I'm going to be assuming that all the maps and paths I'm talking about are smooth, just so that we can talk about differential forms. And the broad idea is that Chen's construction uses differential forms on Rn to build differential forms on the path space. And where the connection to the path signatures are is the fact that these path space monomials arise as the Chen zero cochains. And so this construction of the differential forms in Rn is essentially we're taking a map from the bar construction of the de Rham complex of the underlying space Rn into the de Rham complex of the path space. And we call the Chen construction the image of this map. And so this was originally done by Chen in the 70s, but this was later extended to the setting of mapping spaces by a series of authors. The sort of the first paper that sort of spelled everything out is this paper by Patres and Thomas. And there's a very nice exposition which lays everything out very nicely in sort of in the context of these higher Hochschild complexes in this paper by Ginot, Tradler, and Zanellian. And all of these constructions were done using in the simplicial setting. And so in order to talk about differential forms on spaces such as the path space, we need to extend our notion of what it means to be a smooth space. And one of the concepts that Chen introduced is this notion of differentiable space. And so a differentiable space is some set X equipped with a collection of plots. And so this is just, we can think about these plots as just some generalization of charts for manifolds, except instead of using open sets on Rn, where we use convex subsets of Rn, and there's no restriction on what the dimensionality of these Euclidean spaces are. So these can be convex subsets of any dimensional Euclidean space. And these just have to satisfy some compatibility conditions. So these plots have to be closed under smooth pullbacks. So if a map from C to X is a plot, and we have a smooth map from C prime into C, then the composition is also going to be a plot. It has this covering condition. So if I know that if I have some arbitrary set map from C into X, and I also have these inclusions C1, C2, and C3 into C, such that the compositions are all plots, then I know that this original map from C into X is a plot. And lastly, we say that all points all maps from the singleton into X are also plots. And so we say that a map from between two differentiable spaces is smooth if for any plot phi on X, the composite with this map F is a plot on Y. And so we get a category, of these differentiable spaces. And yeah, so also just a remark, this is very similar to notions of like diffeological spaces, which I think is maybe a little bit more commonly used nowadays. So just to give some quick examples of differentiable spaces, every manifold is a differentiable space just by taking all charts to be plots. And additionally, all mapping spaces between two differentiable spaces is also a differentiable space. The way that we define the smooth structure on mapping spaces is that we say that a map from some convex set into the mapping space is a plot if and only if this adjoint map is also a plot. Since we know what the sorry, I should say that this is smooth, since we X may not necessarily be a convex subset. And furthermore, all limits and colimits are also we can take limits and colimits in this category of differentiable spaces. And this sort of category theoretic perspective is all laid out in a paper by Baez and Hoffnung in 2011. And so we can talk about differential forms on these differential spaces by just assigning a differential form to each to the domain of every plot. So a P form is just an assignment of a P form to the domain of each plot. And specifically, it has to satisfy this pullback condition. So if the differential form on phi composed with F is just going to be the pullback of phi omega phi by the smooth map F. And we can define all the ordinary operations plotwise, and we can obtain a de Rham complex for these differentiable spaces. And so the Chen construction for path spaces can be summarized as the composition of these two maps. So the idea is that we take a collection of differential forms on X. So we choose some collection of differential forms on X, and these can be of different degrees. We compute the pullback of this differential form along the evaluation map to get a form on this M simplex across the path space. And then we integrate the resulting form along this M simplex. So so the resulting differential form is going to be of degree less than the total degree of these differential forms in this tensor product. And to see how we can get these path space monomials, we're going to take X to just be Rn, and these differential forms to be standard one forms on Rn. If we compute the pullback, we find that the pullback is just going to be this iterated product of derivatives of the underlying path, and the resulting zero form evaluated on this path gamma is going to be exactly this path space monomial. And so this is sort of the motivation behind trying to use the Chen's iterated integral cochain construction to get some definition of mapping space monomials from higher dimensional domains. And so earlier I mentioned that there has been some generalizations of Chen's construction to mapping spaces, and all of these were done using simplicial sets. Because we're primarily interested in obtaining monomials for mapping spaces from a cubical domain, and this is primarily for applications reasons. Most data or maps that, a lot of data or maps that are studied are more naturally described using cubical domains rather than simplicial domains. And so the first step in sort of generalizing these path space monomials was to reformulate this Chen construction for mapping spaces in terms of cubical sets. And in particular, we're going to be using this notion of cubical sets with connection. This was, and yeah, so one of the places this was introduced was in this paper by Brown and Higgins in the 80s. And so the cubical sets with connection, I'm going to be introducing it in a specific way here, where I'm going to define this box category with connections as a category internal to the category of differentiable spaces. The objects are just indexed by natural numbers, just like simplicial sets, and they're equipped with morphisms, which are the coface maps, the codegeneracy maps, and also these co-connection maps. So, I mean, I guess the coface and codegeneracy maps are fairly standard. But it turns out that if we only use the coface and codegeneracy maps, the sort of homotopy theory of cubical sets doesn't work out as nicely. In particular, geometric realization isn't, sorry, the products aren't preserved under geometric realization. And it turns out that by adding these co-connection maps, which we think of as sort of additional degeneracies, we can preserve the product structure under geometric realization. And so this co-connection map is just computed by taking the max between two adjacent coordinates. And so I guess just a remark here is that I'm taking a very specific smooth structure on these n cubes. In particular, I'm saying that if I decompose these n cubes into its constituent simplices, then a map on the n cube is smooth if it's smooth on each individual simplex. So in particular, these I've put a smooth structure on these cubes such that these maximum functions are defined to be smooth. And in particular, we can talk about geometric realization of these of cubical sets in this category of differentiable spaces. And yeah, so a cubical set with connection is just a functor from this box category with connections into sets. And yeah, and we'll get the dual of each of these structure maps. And so now we can talk about the cubical Chen construction for these mapping spaces. And the idea is, the basic idea is the same as what we did in the case of path spaces. We choose a collection of differential forms on X. So at this point, I'm just thinking of X as a manifold or a differentiable space. So we choose a collection of differential forms for each of the P cubes in our cubical set. We compute the pullback of the tensor product of these differential forms along this generalized evaluation map. And how this evaluation map is defined is by taking these evaluation maps for each cube. So this eta A is the natural inclusion of some geometric P cube into the geometric realization of our cubical set. And by composing this smooth map gamma from the geometric realization into X, we get this higher evaluation map that corresponds to the cubical structure of K. And once we have this differential form on the P cube cross the mapping space, we integrate the resulting form along P, and we'll get a differential form on the mapping space of degree P less than the total degree of the original collection of differential forms. And so now that we have this construction, in order to get some definition for mapping space monomials or the mapping space signature, we're going to be looking at the zero cochains of this model. And it turns out that there are a much larger variety of zero cochains for these mapping spaces compared to the path-based setting, simply because there's a much larger variety of the types of differential forms we can choose for these omega A's. Because in the path space setting, all of these were restricted to be one forms. And also there's a lot more degeneracies that occur in these higher dimensional cubical sets. So we're going to be placing some assumptions on the types of zero cochains we're going to be looking at. So in particular, we're taking K to just be the standard cubical set model for the unit D cube. We set X to be just Euclidean space. And we also restrict ourselves to looking at standard D forms to sort of coincide with the case of the path space monomials. And the notation I'm going to be using for standard D forms is just a order preserving injection from the finite set D into the finite set N. And the collection of all of these order preserving injections will index all the possible standard D forms on Rn. And this also restricts the degree P that we're allowing. So the degrees that we'll be considering are just multiples of D. And in particular, this M, which is something that we'll call the level of the signature. So this corresponds to the number of D forms that we'll be using. And in the path space case, this corresponds to just the number of iterations in our integral. And specifically, we're going to be associating these differential forms to specific P cubes. And these are going to be just the degeneracies of the unique non-degenerate D cube. And the specific degeneracies we're going to be using are just going to be indexed using an element of the permutation group. And so this was just sort of a way to say that we're not going to be using all of the zero cochains that arise from this construction, but only specific ones.
In number one, do you mean the cubical set represented by D, or like in the category?
Yeah, so this is okay. Yeah, so maybe the notation is a little confusing here, and sorry about that. So I'm saying that K is the cubical set that represents the geometric D cube. So its geometric realization will be the D cube. So this is the cubical set where the non-degenerate cubes are going to be just all the vertices, all the edges, all the faces, and so on. And so, yeah, sorry, maybe I misunderstood your question.
Okay, so I thought it's like the standard and D simplex in the simplicial set case. So that's the standard cube represented by.
Yes, exactly.
Okay,
yes.
okay.
Yes.
And what was the number M here in number 3? Just you said something about it, but I missed it. Yeah.
Yeah. So this number. So M can be any natural number, but this M is just going to be sort of a different grading that we are using that represents which multiple of D. So this is the number of standard D forms that we're going to be using in this zero cochain.
Okay, so you mean image of P, essentially the size of the image of P, or?
Yes, sorry. So because we're trying to get zero cochains, we need the total degree of this original set of differential forms to be exactly P, so that once we perform this construction, we get E minus P equals 0. So we only consider the case where we look at this construction where P is equal to MD. And therefore, M corresponds to the number of D forms that we'll be using in this construction. So,
okay. I see.
Yeah. So so in the previous construction, I mentioned that we need to choose differential forms for each P cube. And so what I mean here is that we will associate these standard D forms to specific cubes, and everything else will associate just the zero form 1 to it.
Okay, thank you.
Okay, cool. All right. And so with this construction, we can define our analogous notion of these mapping space signatures. And so, so I'm going to start off by talking about mapping space monomials, which are the specific terms in the signature. And so now, now that we've sort of obtained a motivation for how we want to define these monomials, I'm going to return to the setting of Lipschitz maps, primarily because we want to be able to talk about maps of lower regularity than being completely smooth. And this is the setting in which a lot of these definitions are still fairly straightforward to write down. And so the mapping space monomial for a map, for a Lipschitz map gamma is this integral. And I'm going to be defining all of the terms in it now. So in the path space setting, these monomials were indexed using this multi-index I. In this mapping space setting, we're going to have two different indices. There's going to be the forms index, which corresponds to which D forms are we using. And once again, I'm going to be using this P notation to denote differential forms. And there's also going to be a permutation index. And this is something that determines what the domain of integration is going to be. So this is just a collection of D elements of the degree M symmetric group. The domain, this D MD pi, is a product of permuted M simplices. So I'm going to be using boldface T to denote an arbitrary element of this domain, and Ti to just be one element from each of these simplices. And so this permuted simplices, these permuted simplices, given some permutation pi from sigma m, is just an ordinary M simplex, except the order of the individual components are permuted. And this J gamma P is just the Jacobian minor when the map gamma is restricted to the P coordinate the coordinate specified by this form's index P. So we're taking the determinant of this Jacobian minor. So so one way to think about this is that we're taking sort of these multiply iterated integrals of the Jacobians of the underlying map. And we can see that if we restrict ourselves to D equals 1 here, these Jacobian minors end up just being ordinary derivatives. And the domain is just going to be some permuted simplex, a single permuted simplex, and we can get back the path space monomials. And so, and in this setting, we can also talk about some metrics that generalize the metrics that are used when we're talking about the analysis of these paths. Once again, if we look at Rademacher's theorem, this tells us if we have a Lipschitz map from the D cube into Rn, the collection of these Jacobian minors is going to be these Lipschitz maps are going to be differentiable almost everywhere, and this means that the corresponding Jacobian minors are also going to be differentiable almost everywhere. And so we can think about this collection of Jacobian minors as an element of as an L infinity function. And similar to the case of paths, this mapping space monomial is only defined using these Jacobians. And so we can talk about a quotient of these Lipschitz map, which we call Jacobian equivalence. So if we take two Lipschitz maps, we say that they are Jacobian equivalent if their corresponding Jacobian minors are all equivalent as L infinity functions. And we call the space of Jacobian equivalence classes using this tilde. So this equivalence relation corresponds to the translation equivalence of paths. And once again, we can talk about generalizations of the one variation and Lipschitz metrics, which are just going to be either the L1 norm or the L infinity norm on these Jacobian minors. And so the full mapping space signature is going to, we can sort of collect all of this information together into a single map from these Jacobian equivalence classes of maps into this Hilbert space HD. This is sort of an extended tensor, something like an extended tensor algebra. This doesn't have, at this point, we're thinking of this as just a Hilbert space without an algebraic structure. But I'm going to use these double brackets to just mean it, to specify that it means something like a power series. And really, this is just the collection of all possible pairs of the forms index and the permutation index for any natural number n. And so this is part of the joint work with Chad Giusti at University of Delaware, Vidit Nanda at Oxford, and Harold Oberhauser also at Oxford. We find that the mapping space signature has many of the properties that ordinary monomials and the path space monomials have. In particular, it is continuous with respect to this the Jacobian Lipschitz metric. At every level m, this mapping space signature has factorial decay. In particular, the image of this map has bounded norm, and this is how we can actually talk about this HD as a Hilbert space. It's coordinate-wise reparametrization invariant. So if I reparameterize each of the coordinates in our map independently, then this mapping space signature is going to be invariant under these types of reparameterizations. It also has two different equivariance properties. So it's equivariant with respect to the hyperoctahedral group action on the domain. So this is just all the symmetries of the D cube. So in the one-dimensional case of paths, this group just has one element, which is time reversal. And we found that in the setting of paths, we can talk about the signature of inverse path as its tensor inverse. So we can also explicitly write down what, if we apply this group action to the domain, we can also obtain the corresponding signature as other elements of the as other monomials that are already computed. And additionally, it's also equivariant with respect to the GL n action on the codomain. And this is precisely because these are simply integrals, and there's a corresponding induced action on this Hilbert space. And lastly, we also have an algebraic structure, sort of an internal algebraic structure of these monomials, which is a generalized shuffle product structure. And in particular, we can take these finite linear functionals. So here, the single brackets means I'm not taking power series. So these are going to be finite linear combination of elements in here. We can view this as continuous functions from these Jacobian equivalence classes into R, and this forms a subalgebra of the algebra of continuous functions. And this is sort of, once again, the the first hint that the terminology mapping space monomials is justified because we have some sort of algebraic structure on these functions. And furthermore, we can once again talk about a normalized variant of this and parameterized, normalized parameterized version of this, where what I mean by parameterized here is that we're taking these Lipschitz maps and appending the parameterization to the underlying map. So I'm extending these Lipschitz maps in Rn to some map in Rd plus n. And if we append this additional information, take the signature and then normalize it, then we find that it also has similar properties to the path signature. Specifically, it's continuous and injective. It is universal with respect to continuous bounded functions on these mapping spaces. And it's also characteristic. So the expected mapping space signature is going to be injective with respect to finite regular Borel measures on these mapping spaces. And so just to wrap things up, what we did in this work was we used the framework of Chen's iterated integral cochain construction to build some notion of monomials and signatures for mapping spaces. And I mentioned at the beginning that this primarily has applications in two different settings. One is in machine learning. So we hope that with this definition, we can use this to talk about feature maps. We can use this as a feature map for parameterized data and develop kernel methods to for these types of parameterized data, potentially for possibly like classification applications. And additionally, this might have applications in stochastic analysis, where we may be able to, I guess, in current work, we're trying to think about how we can develop higher dimensional notions of things like rough paths. So can we develop higher dimensional rough integration theories? And furthermore, we can talk about certain extensions of this work. Sort of connected to this application in stochastic analysis is to look into how we can go beyond this Lipschitz restriction. So in the case of the path signature, it turns out that we can actually go beyond the Lipschitz restriction a little bit without having to use the machinery of rough paths, and we're hoping to see that we can have a similar extension for these mapping space signatures. And also we can consider maps on manifolds. So when I talked about Chen's cochain construction, this was very general, and the codomain could have been any manifold. We could take some D forms in these manifolds and potentially construct similar monomials for maps on manifolds. So thank you very much for your attention. And this is currently work in preparation, and we're hoping to get this up on the archive in a couple of weeks. Thank you.
Thank you, Darrick. That was nice. That was great. So any questions for Darrick? Okay, yeah, so maybe I can ask, so in the context of applications, so why are cubical sets more natural than the simplicial ones?
I guess just primarily, it's not that necessarily the fact that the cubical sets are more natural, it's the fact that data that, maps from a cubical domain into some other space is a little bit more natural. So an example for in machine learning would be data that takes the form of like images or videos. These are normally in sort of these rectangular domains, and we can think about Yeah, so we can think about this data in a little bit more natural way. Another maybe more theoretical reason why we want to look at cubes rather than simplices is that there are more natural composition structures. So something that I didn't talk about for the mapping spaces is some analog of Chen's identity, where we said that the concatenation of two paths, we can compute the signature of the concatenation by the tensor product. And so with cubes, with a D cube, there are D concatenations that we could perform. Whereas with with simplices, this is a little bit harder to define. It's not as natural to do. And this is actually something that we are currently working on and thinking about how we can get some sort of structure or whether there exists some structure in the mapping space signature that that is coherent with the composition structure of these maps from D cubes.
That is what I was going to ask about for Chen's formula. That of course in topology, if you have these D different compositions where you put cubes horizontally or vertically or the D different directions, then there are homotopy commutativity results saying that that these are basically homotopic, and so that everything is homotopy commutative.
Yeah.
So do you expect something like this? I mean, I'm seeing that for points and paths, you're getting symmetric algebras and tensor algebras, and so one might expect that for default compositions there might be some kind of algebras related to, well, these little D cubes operand type algebras. So
yeah.
Interesting. If you not only get D, I mean, in the cubical picture you can probably get your D different compositions corresponding to some, but then there should be some. It would be interesting to know if you could pick up some interaction between these, or relations between those.
Yes, I think this question is this is a really great question. I think it's something that's really interesting and something that we are currently working on. So I think that the sort of the homotopy theoretic perspective is a little bit too coarse in what we're trying to do here. Primarily because I mean, if we're thinking about these compositions in terms of the little cubes operand, there's too much flexibility in how we can sort of compose these different cubes. And I don't expect something to be in some product structure to be invariant under all of these homotopies. I would expect that we would get D different composition structures that, I mean, hopefully we can get D different composition structures that somehow relate to some higher dimensional version of the tensor algebra. But yeah, I think that's a really interesting point.
Yeah, even if they're not actually equal, there might still be, I mean, if D is 2, there's kind of a circle of possible compositions where you now know about 2 or 4 points in the circle, and the fact that they're somehow connected in a loop it feels like it's some extra information, even if it's not actually homotopy invariant. Anyway, yeah, that sounds great. Thanks.
Yeah, thanks for your question.
Okay, any other questions for Darrick? Okay, perfect. Then let's thank Darrick for this. Okay, so thank you very much, Darrick.